Welcome to Data Science 1, Probability, Students' T-Distribution. Things we're going to need to remember, we're going to need to know about the cumulative distribution function, the probability density function, the chi-square distribution, and the standard normal distribution. And as we move along through these videos, you'll see that as we get deeper and deeper and deeper, things require on items that we've learned before. All right, so this distribution and the next distribution is really difficult to motivate from a type of experiment where we're looking for Bernoulli trials or waiting times or things like that. Here we're just going to go straight forward and tell you what we're looking at. So in statistics, you're going to find a one sample hypothesis test on a mean statistic given by this formula. You may have ran across it already. And here, x bar is the observed sample mean, s is the observed sample standard deviation, and n is the number of samples. The question is, do we know what probability distribution this thing has? Because if we do, then we can use that to match it up against real data and the theoretical answers that we get from probability and see whether they agree or not. So here's how we're going to set this up. So suppose z is normal 0, 1. And x is chi-squared nu degrees of freedom. Z and x are independent, then t equal to z over the square root of x divided by nu. We get a t with nu degrees of freedom. This is what it's defined to be, where t with nu degrees of freedom is the degrees of freedom are our parameter again, as just like from the chi-squared. Now look at them together and you can see, if you go back and look at the other videos, I'd look at this formula. We had a z transformation that had an x minus mu in it. And then here we have a square root, which has a square root. We have something squared. And remember, this chi-squared is a normal squared, something squared divided by a number. So this looks like it could be potentially good, and it's actually what it works out to be later. Okay, so here's the density of the distribution, and you can see bits of the normal distribution hiding into the square root of nu pi, and you can see parts of the chi-square distribution hiding in here with the gammas of nu over 2, things like that you've seen before, okay? But we're not going to go through and derive all of this, but it has a mean and variance. The mean is 0 as long as nu is greater than 1. If it's equal to 1 or 0, then it's either infinite or it's undefined, so we're not going to talk about that. Here the variance is nu over nu minus 2, so nu better be greater than 2 because variances always have to be positive. So it's either undefined or infinite if it doesn't meet that criteria. Okay, so let's look at the shape of the T1 distribution versus the standard normal distribution. They're both symmetric, but what you really notice is that the normal is much more peaked at the top, so it's far more likely here than what the T would say. But the real difference is out here in the tails. So these are called the tails here. Out here in the tails, remember, area and probability are the same. So if you look at the blue, this is the probability for the normal, and if you look at the pink, this is the probability for the T. There's a lot more area and more probability out here in the tails, and that's really what we're interested in because this extra area in the tails gives us the ability to handle the variation due to estimating both x bar and the standard deviation. Okay, so what does the degrees of freedom do to the shape? And I'm going to roll through a couple of these. Let's see, here's one, and notice what happens between 1 and 2. It becomes much more likely here, and the tail starts pulling in some. Okay, so you can see that. See, we go from 1 to 2. Then it happens again from 2 to 3, 3 to 4, 4 to 5, and notice how close it's getting to the normal distribution just with 5 degrees of freedom. Here at 10, there's close, but there's still difference out here. You can see the difference here, and it doesn't match at the top. So let's make a bigger jump to 50. And here it's harder to see, but you can still see some red over here, meaning that red is sticking out farther than the blue, and you can see some red under the blue here. Then at 100, it looks pretty close. So, and also we know that as nu goes to infinity, it becomes approximately normal 0, 1. So we know this is going to happen. That means if we have like 1,000 degrees of freedom, we'll just use the normal table because we might as well, because they're basically the same distribution at that point. All right, we're going to use the computer. because working with that distribution is a little bit tough. So if we have a given value of x and degrees of freedom df, then in R we would use pt, put in your value of x you're interested in. Remember, the CDF is the area to the left of the value, lower than the value. And the degrees of freedom is going to spit out that probability for you. If you're in Excel, you're going to use t.dist, same x, degrees of freedom, but you're going to add true so that it gives you the cumulative distribution, because otherwise it'll give you the density, which is not useful. The inverse CDF is for a given probability P and degrees of freedom DF, we would use in R QT. P and DF are the entries that we would put in it, and it will spit out the X value that we're interested in. And in Excel, we're going to use T.INV with P and degrees of freedom. Now, we use these more in later videos, but I'm giving them to you here just to show you that you're not going to be having to integrate this crazy thing on your own. All right, so quick review here. This is the density. Here's the mean. Here's the variance. Has conditions on it when it exists and doesn't exist. Kind of freaks people out when you tell them distribution with 1 degree of freedom has no mean or variance. People go, what? It's true. It's a distribution that has no mean or variance. Okay, so here the CDF is too difficult, so we're going to use a computer to handle this. So don't panic. It'll be easy to do. And we're going to move on to the F distribution in the next video, so see you there.